Hello class, welcome to today's lesson, which is the last lesson for the first topic. It's the last lesson for the first, let's say, subtopic of calculus, which is, remember, the limit, the concept of limit, and the concept of the derivative. Okay, in this class, we're gonna finish what we had in the previous lesson, which is the definition of the derivative. If you remember, I did not want to define it in that lesson because it was already too long in regards to time, and I decided to stop it for the moment. So now today we're just gonna define the derivative, and that's it. That's what we're gonna do today. It shouldn't be a long class. Okay, so what is the derivative? So let's recapitulate about what we did in the last class, which I told you was the most important of, probably the most important of the whole course. So what do we have here? Here we have four Cartesian planes. In yellow, I'm giving you the graphs of four different functions. In this one, we have a parabola for the function f of x equals x squared. In this one, we have the cubic function, which goes more or less like this, and then it goes downwards in the same way. For this one, we have the exponential function, and in this one, we have the function square root. I'm giving now different names to the functions because it's not always f, okay? Don't get used to say f of x. It can be g of x, h of x, t of x, whatever. It doesn't make any difference. Whatever letter you name the function, it's perfectly fine. There is no problem. Okay, and what else am I giving you besides the graphs of these functions? I'm giving you a point in them. Can you see? In each of the functions, I'm giving you a specific point. And for that point, we have the coordinates 2, 4, right? This is the value of the independent variable, and this is the value of the function, right? Because 2 to the square is 4, and so on for each of them. You see, 1/2, the value of the function is e to the 1/2, and here we have 9, and the value of the function is 3 because this function is the square root of x. So evaluate it in 9, you should get 3. Okay, and in those points, what do we have? What we observe is 4 lines, which happen to be the tangent lines, okay, to each of these functions at those specific points, the tangent lines. And if you remember well, what we did in the last class was getting the slope, okay, slope. That's what we were trying to get. The slope of the tangent line to a function at a specific point. That's all we did. That's all we've been doing for the last 2 or 3 classes. Okay, why? Because that's a very important problem. You may not know the importance of such problem yet, but you will throughout the course. And what did we do? We said in the end that basically by following this formula that we found by a process of reasoning, of reasoning about the slope of the second line and some limiting process, we found this very specific formula, okay? And I told you how to read it, more or less, okay? It doesn't have to be read in this way, but it's a good way to read it. And well, let me correct in here a little bit because I want it to be very clear. Like so. Okay, I told you that all of this is read as follows. The slope, this little thing here, this apostrophe, it's you could read it as the slope of the tangent line to the graph of f at point x. Okay, repeat that part as many times as you want in order to burn that into your brain. Okay, you have to read it that way. Equals the limit as h approaches 0 of this particular quotient, f of x plus h minus f of x over h, where h is called the increment in the context of calculus. And once we do this limit, we can find a formula most of the times, right? most of the times it's very easy it's kind of easy to find a formula. And in the case of for the squared function or the quadratic function, sorry, we found that such formula yielded this. Okay, the slope of the tangent to the graph of f at point x is equal to 2x. So if I want to find simply the slope of this tangent, which is at point 2 comma 4, all I need to do is substitute this value of x, which is 2, in this formula, and I would go like this. uh, 4. So the slope of this tangent to this graph of this function at this precise point 2 comma 4 is going to be 4. Okay, so that's how we can find the slopes of tangents to functions, by following this little formula. Okay, so far, and the same is for all the other. Okay, look at the formulas. Obviously, taking the necessary changes, instead of f, it's gonna be g, because in this case the function is called g. Instead of f, it's gonna be t, because in this case the function is called t. And let me tell you why I didn't write anything here. If I call the function h, look at this. I'm calling it h of x equals e of x. If I do that, I'm gonna run into a problem, right? When I write the formula, because I'm gonna be like, okay, I'm gonna write this equals the limit as h goes to 0 of, let me erase this, of h of x plus h minus h of x over h. And it's not a good idea, because it's not a good idea in mathematics to call, under the context of some problem, having named two different things by the same symbol. Okay, in here this h represents the increment, in here and in here, and in here this h represents the function. So this is a very bad idea, very bad idea. So either you change the name of the increment for any other letter, which is perfectly okay, it doesn't have to be called h, or you change the name of the function, okay, in order to have proper and consistent mathematics. Okay, that was just a bonus. Okay, guys, so far the only thing that we have done basically is found the slope of a tangent to a function at a certain point x, and this is the most important formula that we have discovered. Okay, now let's go on to define the derivative. Here is the definition, very important definition. Write it down somewhere in your notebook or any other place that you're having. Okay, so definition of the derivative, sorry, of a function f at, well, no, it's just at x. Okay, this is the whole phrase. We're gonna define the derivative of a function f at x, and it's gonna be the following. You're gonna be surprised, because I'm gonna write exactly the same formula as before. Can you see? Exactly the same thing. You see? This is the formula that we found for the slope of the tangent to a function at a point x, or at x. And why do I say that this is gonna be called the derivative now? Okay, let me tell you why. It's very important for you to understand why. Just write it down for the moment, okay? Like so. Okay, let's go here for a moment. Okay. In mathematics, guys, it's often the case that mathematicians encounter in the working of the problems some objects, and they come up so often that they decide to give these objects or yeah, these objects a specific name. What do I mean by this? I suppose by now you have seen this concept, the concept of factorial. Okay, this number. For example, when we say n factorial, which is the multiplication or the product of all the integers, 1 times 2 times 3 times 4 times etc. up until n. Okay, this is all of this product is defined as n factorial, and we give it this symbol n and then this sign. Okay, why did mathematicians call, or why did mathematicians name all of this product by this curious name, the factorial of n? Why give it a proper name, a specific name? Because of the following. This number or this product appears so often in mathematics. For example, I'm going to give you 3 examples for this. Look at this one. The number of different ways to arrange 4 people along a line is 1 times 2 times 3 times 4. Okay, if you have 4 people, let's call them A, B, C, and D. You can arrange them along a line. For example, this is one arrangement, A, B, C, D. That's one arrangement. Then I can go like A, C, B, D. That's another arrangement. A, B, D, C, etc. Okay, I don't have to go on like that. So how many different arrangements do you have? You have 1 times 2 times 3 times 4, which is 24 in the end. Okay, and mathematicians discovered this a long time ago. Okay, so fine, perfect. Now, what is the coefficient of the 5th term in the binomial expansion of x plus 1 to the 12th? Okay, you know how to perform these things already. Okay, and the coefficient of this term, of the 5th term, is given by this. Okay, the product of 1 times the next integer and so on up until 12 over this product right here times this product right here. You see, so it's basically the same idea. It's the product of integers from 1 to a final number, from 1 to 4, from 1 to 8, from 1 to 12. So another case of this particular product coming up in apparently different problems. Okay, problem 1 and problem 2 sound different. What about this? Well, they're not problems, they're examples. And what about number 3? Look, the exponential function e to the x can be calculated by using an infinite series of the form. Look at this. I don't know if you have seen this before. E to the x, if you want to calculate it by hand and not use a calculator, you can use this series until infinity. Of course, you're gonna stop somewhere, and all you will get is an approximation, but it could be a good approximation. But I want you to look at the denominators of this formula. Look, x to the 0 over 1, x to the 1 over 1, x to the 2 over 1 times 2, x to the 3 over 1 times 2 times 3, and so on for all the fractions. And this goes on forever and ever and ever. You see? So again, the product of the integers, of all the integers from 1 to a final number, appear also in this formula. So why is this product so special? Why does it come up so often? Okay, mathematicians realized or noticed this fact, and they decided to give it a proper name, because they said, okay, this idea of the product of integers from 1 to whatever number at the end comes so often that it's a good idea to give it a name, because in order to facilitate things and not call it the product of 1 up until another number. And so let's give it a number. Let's say this. Instead of writing 1 times 2 times 3 blah 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 up until 12, we're gonna say 12 factorial, and I'm gonna represent by this symbol this idea. Okay, so 12 factorial will be equal to 1 times 2 times 3 times etc. up until 12. You see, so it's a much more manageable way to write a very large product. Okay, so that's how many mathematical objects began. you look at some examples from different fields in mathematics or different branches, and if something comes up very often, mathematicians get curious about that object, they name it, or as I say, they baptize it, they give it a proper personality, they produce a symbol for such concept, and they start to study it on its own as a proper object of study, regardless of the applications, regardless of all of these examples. Mathematicians don't care about examples, they care about the object itself, like the factorial, and they start to analyze it mathematically without any regards to applications whatsoever. So that's how the concept of the factorial was born. Now, how is this related to what I'm teaching you right now? I mean, because it seems like it has nothing to do, right? Okay, let's close this. I just gave you about 5 minutes ago the definition of the derivative, and I said the derivative of a function f at point x, which is read like this. I'm gonna repeat this symbol. The derivative of f at point x. That's how you read this. Okay, I know that I told you before that this can be read as the slope of the tangent to the function f at x. Okay, that is okay. That's not wrong. But in the context of the derivative, we're gonna call it the derivative of f, the derivative of f at x, and it's going to be the limit as h goes to 0 of this quotient. Okay, and let me tell you what is the connection between what I said about factorials and this definition. Why did I bring up the factorials? Okay, how did we discover this particular formula? How did we discover it? By solving the problem of finding the slope of the tangent to a function f at the point x. That's how we found this formula. Now, mathematicians discovered that formula under those circumstances. And then what happened was that as time went by, mathematicians started to see this very formula under other problems. You see, under other circumstances. You see, so they said, okay, there is something peculiar about this formula. It's not only about slopes. It has to do about changes, rate of change, velocities of objects, and so on. In many different places, this formula started to appear. So they said, okay, this I want to baptize this under a different name, not just the formula for getting the slope of a tangent, and I'm going to call it the derivative, okay? I'm going to say that this limit, this precise limit, is the derivative of the function f at point x. I'm going to repeat one more time that. All of this symbol is read as the derivative of f at x. And what is that equal to? This limit. The derivative of f at point x is equal to this limit. That is the definition of the derivative. And now this concept takes a personality of its own, and it can be studied as a mathematical abstract object without making reference to slopes or to whatever other problem that gave rise to this thing. I don't know if I'm being clear. You can ask me in a moment if you're confused about what I'm saying. Okay, so that's basically the definition of the derivative. This is the definition, guys, of the derivative, and like I said, it's one of the most important formulas for the course, and that's basically it. Maybe I'm gonna give you as a final remark another way to read all of this, okay, which is the following, a quicker way, because saying the derivative of f at x is way too long. So most mathematicians read this as follows: f prime of x equals blah blah blah. Okay, the important part is here. The important part. F prime of x equals this. The derivative of f at x is equal to this. And in the context of getting the slope of a tangent, you can say it as the slope of the tangent to the function f at point x. You see? But that's only under the context of the slope. This object has its own personality. It's called the derivative. And that's what I want you to understand. It's an abstract mathematical concept. Okay, we're going to stop it right there. And I want you to solve the problems or the exercises for this lesson. So that's it, guys. Thank you.